guys, listen up. This is coming from a second-year physicist. You really don't know what's coming for you this year. Classical mechanics is a pretty difficult module to swallow, just like Lancaster's terrible jokes. That being said though, if this video can help you with your conceptual understanding of Coriolis forces, then we've been happy to help.
Okay, you gotta catch it, yeah?
Oh, where did it go?
Okay, wait, that was weird.
So why does it look like the ball took a different path than what we would typically expect? Let's slow the video down and have a closer look. We see here that person A is throwing the ball straight to person B, sitting opposite, while the merry-go-round is rotating. Although person A intended to throw the ball straight to person B, we can clearly see that the ball misses its target. What makes fictitious forces special is that their very existence depends on the observer's frame of reference. The frame of reference is simply a set of physical reference points relative to which motion can be measured.
So as soon as we step onto the rotating merry-go-round, we move from an inertial to a non-inertial frame of reference, assuming the merry-go-round is rotating, of course. So person A and person B are convinced that the ball curved and will both agree that a force acted on the ball to curve its path. However, an external inertial non-rotating observer would see the ball following a straight path without any external forces acting on the ball. So, Teresa, our non-inertial observer, sees the merry-go-round rotate under the ball, with the ball's trajectory unaffected while in the air. Let's have a look at the rotating frame of reference. In this diagram, we have the axis of rotation, omega hat, the radial direction, r hat, and the angular direction, theta hat. Since we're working in polar coordinates, we can express the radial direction and angular direction as follows. We can also derive expressions for the time derivative of r hat and theta hat. We can also differentiate the non-inertial position vector to find the non-inertial velocity vector. Which we can rearrange in terms of velocity in the inertial frame. Differentiating this expression again gives us the acceleration in the inertial frame, which can also be rearranged in terms of acceleration in the non-inertial frame. Other two terms are the Coriolis and centrifugal accelerations. Since force equals mass times acceleration, obviously, we can multiply the expression of acceleration by mass to give us the force in the inertial and non-inertial frame of reference. This equation also contains expressions for the Coriolis force and centrifugal force, which is outlined in this equation. So that's the Coriolis force broken down.
So that's the Coriolis force broken down. But just so it clicks a little more, I'm going to give you guys some examples of the Coriolis force in action in nature. It has a significant effect on our weather and causes winds and storms to rotate in a counterclockwise direction in the northern hemisphere and clockwise in the southern hemisphere. Now in this example, we have the Donald, credit to Lancaster for the name, and has decided to assassinate the president of Cuba, Raul Castro. Donnie is firing a rifle from Washington DC downwards, straight at Raul's head, all the way in Havana, separated by a distance of around 1,800 kilometers. Of course, Donnie has no idea what the Coriolis force is, among many other things, and just aims straight for Raul's head. But due to the effect of the Coriolis force, the bullet will miss its target and instead strike a poor cigar maker just west of Havana. Quite sad, really. We hope this video helped you guys, and just good luck in classical mechanics, honestly, like, just good luck.
I suggest a new strategy.